Objectives. The aim of this lesson is to make the user to understand optical properties of minerals. Minerals are characterized by certain definite optical properties, and these properties serve as a basic tool for the identification of minerals under the microscope. The following are the objectives of learning this module. Importance of optical properties. Various optical properties to understand the identification of minerals, followed by conclusions. After attending this module, the learner will be able to practically apply the optical properties in the identification of minerals. Introduction. Minerals are characterized by certain definite physical properties, chemical composition, optical properties, and internal molecular structure. The study of minerals is made under different heads like physical mineralogy, chemical mineralogy, optical mineralogy, and X-ray mineralogy. The properties such as Pleochroism, extinction and extinction angle, twinning, and accessories of transmitted light microscope are all dealt under the head optical mineralogy. Optical mineralogy deals with the study of optical properties of minerals in thin sections and grains under a special type of microscope called petrological microscope. There are different optical properties which aid in the identification of minerals. The most prominent of these are color, shape, cleavage, relief, alteration, exsolution, pleochroism, interference color, extinction and extinction angle, twinning, refractive index, twinkling, and birefringence, etc. These are important for the identification of minerals individually and also when they are the constituent of the rock. Color. Deeply colored minerals in hand specimen are likely to be also colored in thin section, although typically the color is much stronger in hand specimen than thin section. The more strongly colored minerals are often relatively iron-rich or rich in other transition metal ions. Example, titanium, manganese. Hence, the color of a mineral may be quite sensitive to mineral composition. The color of a mineral is caused by absorption of certain wavelengths of incident white light. The resulting transmitted light lacks these particular wavelengths. Common colored minerals include biotite, amphibole, pyroxene. Opaque minerals do not transmit light and are typically oxides or sulfides and rarely form large proportions of any given rock. Common opaque minerals include magnetite, ilmenite, pyrite. Shape. The shape, form, or habit of a mineral will typically reflect its crystallography. Thus, sheet silicates tend to form sheets, chain silicates will form elongate or needle-like grains, and cubic minerals will typically be equant. This reflects the relative stability of various crystal faces. The shape will also be controlled in part by how easily the mineral is able to grow with an ideal form. Igneous minerals that have grown from a melt will typically be able to form well-shaped euhedral crystals, especially if they grow at an early stage during cooling before the rock becomes too crystal rich. Metamorphic crystal growth occurs in the solid state, and so crystals will be competing for space with each other. In such instances, those with strong preferred crystal form tend to be more euhedral. Clastic sedimentary rocks tend to contain broken or rounded grains. Common well-shaped euhedral minerals are micas, muscovite and biotite, occur as sheets, amphibole which occur as needles, pyroxenes which occur as prisms, and garnet which occurs as equant grains. Common poorly shaped anhedral minerals are calcite, quartz, and plagioclase. Cleavage. Cleavage will appear as sets of parallel lines in thin sections. Cleavage is an ability of the mineral to crack along well-defined crystallographic planes within the lattice structure. Hence, cleavage planes are frequently oriented parallel to crystal faces and edges of euhedral crystals. Sheet silicates, example micas, muscovite and biotite, tend to have one excellent cleavage. Chain silicates, example amphiboles and pyroxenes, have two cleavages, and framework silicate, example feldspars, plagioclase and K-feldspar, and carbonates, example calcite, often have three cleavages. Not all individual crystals will display cleavage, depending on the orientation of the crystal and the quality of the cleavage. Micas have one excellent cleavage, but this will not be seen when the thin section is cut parallel to the orientation of the sheets. Similarly, elongate sections of amphibole will typically show only one cleavage. Minerals with relatively poor cleavage, such as feldspars, often will display cleavage best towards the edge of a thin section, where the rock is typically a little more fractured during the production of the thin section. Relief. Certain minerals stand out more clearly in the thin section than others. This relative visibility of mineral outline is known as relief. Relief is linked to the refractive index of the mineral, the speed at which light passes through the mineral, relative to the speed it passes through the resin used to make the thin section. The greater the difference in refractive index between the mineral and its nearest neighbor, the higher the relief and greater the visibility. Common high relief minerals: garnet. Common low relief minerals: quartz, plagioclase, K-feldspar. Some minerals, example calcite, transmit light at different speeds depending on the orientation of the crystal lattice. Thus, relief changes when the microscope stage is rotated. Relief is the contrast between a mineral and its surroundings, high versus low. Also true in thin sections relative to epoxy or other minerals. If a grain is in a liquid, some light rays bend towards the medium with higher refractive index. Light interacts with the grains as if they were small lenses. If N mineral is greater than N liquid, rays are refracted and converge after passing through the grain. We can see this feature if we slowly lower the microscope stage, shifting the focus to a point above the mineral grain. A bright narrow band of light called a Beckey line appears at the mineral-liquid interface and moves towards the material with the higher refractive index. A complementary but harder to see dark band moves towards the material with the lower refractive index. The same thing can be repeated in a thin section by focusing and at a grain boundary. In order to identify the refractive index of unknown mineral grain, oils with differing refractive index are used. Alteration. Minerals formed in high temperatures frequently show alteration to minerals that are more stable at low temperatures during cooling. The latter tend to be minerals that are hydrous with OH groups in their mineral formulae. Typically, the high-temperature minerals form large crystals and are surrounded by a rim of an aggregate of fine-grained, low-temperature minerals. Common minerals that form at high temperatures: olivine, pyroxene, amphibole, biotite, garnet. Common minerals that form as alteration products: chlorite, muscovite, clay minerals. Exsolution. At high temperature, some minerals may incorporate a range of different elements in their crystal lattice. However, on cooling, these lattices may become more stable if a physical separation into two mineral phases occurs. Thus, some minerals tend to like to be homogeneous mixtures at high temperatures, but will separate at lower temperature if the rate at which they cool down is sufficiently slow to allow the separation to be effective. In such circumstances, The host mineral may exsolve small crystals of the other mineral and a distinctive texture will result. Such X-solution textures are most readily observed in cross-polars as host and exsolved minerals often have rather similar optical properties and so may have similar relief. Common minerals that show X-solution textures: feldspars, plagioclase and K-feldspar, pyroxene, clinopyroxene and orthopyroxene. Pleochroism. Minerals are white or colorless when pure. When color is present in minerals, it may be due to minor impurities, in some cases found as inclusions. But mostly, the color of a mineral is due to its own property of absorbing light of certain wavelengths from white light, the remaining wavelengths being transmitted. In isotropic minerals, since light travels with equal velocity in all directions, its vibrations are equal in all directions and the absorption for any color of light is the same in every direction. Therefore, there is no change in color when the microscope stage is rotated. In anisotropic minerals, ordinary and extraordinary rays travel not only with different velocities but also with different absorption effects. In anisotropic minerals, in which white light is resolved into two sets of vibration, fast X and slow Z, that is, uniaxial minerals, the ordinary and extraordinary rays have unequal absorption power, resulting in the change of color along the fast and slow vibration directions under plane polarized light without analyzer. In biaxial minerals, however, light is resolved into three sets of vibration, X, Y, and Z, and the unequal absorption power of the ordinary and extraordinary rays result in the color change along these three vibration directions. This property of a colored mineral in which the color change is observed under plane polarized light is called in general pleochroism. Pleo means many and chroism means color change. In uniaxial minerals, the color change along the vibration directions is twofold, since there are two vibration directions, X and Z, and it is called dichroism. But in biaxial minerals, the color change is threefold, since there are three vibration directions, X, Y, and Z, and it is referred to as pleochroism. Isotropic minerals are not pleochroic or dichroic, since there is no color change at all. Pleochroism is normally expressed as a formula or scheme by relating the color changes to the different vibration directions as follows. Tourmaline, X, colorless, pale yellow, Z, pink, green, blue. Therefore, the pleochroic scheme is Z is greater than X. Hornblende, X, pale yellow, Y, green, Z, bluish green. Hence, therefore, the pleochroic scheme is Z is greater than Y, which is greater than X. For determining pleochroism of a mineral, it is necessary, first of all, to determine the different vibration directions in the mineral by the usual method. Each of these vibration directions is next brought parallel to the vibration plane of the polarizer, horizontal crosswire or vertical crosswire, since this property is observed in plane polarized light only. The colors noticed in these positions are recorded and finally related to the particular vibration directions. Thus, the pleochroic formula or scheme is derived. After the derivation of the pleochroic formula, the degree of absorption along the different vibration directions is estimated by observing the intensity of the pleochroic colors present along these directions. For example, in the case of hornblende, which shows the pleochroic scheme X equals pale yellow, Y equals pale green, Z equals bluish green. The color of lowest intensity, least absorption, namely pale green, appears along X, and the color of greatest intensity or greatest absorption, namely bluish green, appears along Z. while pale green color of intermediate intensity appears along Y, and in this case, the degree of absorption is expressed as Z is greater than Y, which is greater than X. This expression indicating the degree of absorption is called the absorption formula. Hence, the pleochroic scheme in minerals is recorded by expressing the pleochroic formula accompanied by the absorption formula. Interference colors. When white light passes through an anisotropic mineral, all wavelengths are split into two polarized rays vibrating at 90 degrees to each other. Different colors have different gamma, so some colors may be retarded, though most will not. When the north-south component of the two rays are combined at the upper polarizer, convergent interference occurs for some colors and divergent interference for others. If we see a mineral of uniform thickness under crossed polarized light, we see one color, the interference color. Depends on retardation, orientation, birefringence, and the thickness of the crystal. Interference colors change intensity and hue. As we rotate the stages, they disappear every 90 degrees. Normal interference colors are shown in a Michel-Levy color chart. Very low order interference colors, retardation of less than 200 nm or nanometers, are gray plus white. The interference color of a mineral with very low birefringence changes from white to black every 90 degrees. Minerals with slightly greater birefringence show yellow, orange, or red interference colors upon rotation. Retardation of 200 to 500 nanometers equals first order colors. As retardation increases further, colors repeat every 550 nanometers, average wavelength of visible light, going from violet to red, second order, and then from violet to red again, third order. They become more pastel as order increases. Fourth order colors appear white. Calcite, delta equals 0.172 with high order pastels, and quartz, delta equals 0.011 with first order gray white. If in doubt, insert a full wave plate. Delta's first order white to yellow or blue, but has no effect on high order white. Some minerals have anomalous interference colors due to high dispersion or if they are deeply colored. Chlorite, epidote, zoisite, jadeite, tourmaline, sodic, plagioclase. Uniaxial and biaxial minerals. Isotropic crystals have the same refractive index in all directions because they have the same light velocity in all directions. Anisotropic minerals do not. For uniaxial minerals, we need two indices of refraction to describe the mineral refractive index, epsilon and omega. For biaxial minerals, we need three, alpha, beta, and gamma. Optic axes are directions that light can travel through a crystal without being split into two rays. In some uniaxial minerals, the optic axis is parallel or perpendicular to crystal faces. In biaxial minerals, the two optic axes rarely are parallel or perpendicular to crystal faces. Light traveling parallel to optic axis of a uniaxial mineral travels as an ordinary ray with a unique refractive index, omega. Light traveling in other directions is doubly refracted in two ways. Omega and epsilon refractive indexes. Epsilon is the value between epsilon and omega, light perpendicular to optic axis. If omega is less than epsilon, equals uniaxial positive, and if omega is greater than epsilon, then uniaxial is negative. Maximal possible birefringence is delta is equal to omega minus epsilon if optic axis is parallel to stage. Extinction and extinction angle. Extinction is an optical property of an anisotropic mineral by which the mineral shows darkness in the field of view under crossed nicoles. Extinction occurs whenever a vibration direction of the mineral coincides with or is parallel to a crosswire under crossed nicoles, and a mineral shows four such positions of extinction at intervals of 90 degrees during a complete rotation of the microscope stage. In between these positions of extinctions, the mineral shows illumination with interference colors. But in positions at angles of 45 degrees from the extinction positions, the illuminations shown by the mineral are again at intervals of 90 degrees, alternating with the extinction positions during the complete rotation of the stage. The type of extinction shown by the minerals is determined as follows. The given mineral section is fixed on the stage of the microscope with its prominent edge or cleavage lines parallel to any of the crosswires, horizontal or vertical, and the stage reading is recorded. Let us suppose the reading is 0 degrees. Then the mineral section is observed under crossed nicoles. If the mineral section shows darkness or extinction, the vibration of the mineral coinciding with the crosswire, that is, the extinction direction of the mineral, is parallel to or coincides with the crystallographic direction indicated by the edge of the cleavage lines of the mineral. This type of extinction is identified as the straight or parallel extinction. Then the stage is rotated through an angle of 90 degrees. When the stage reading is recorded 90 degrees, and in that position it is noticed that the edge or the cleavage lines is parallel to the vertical crosswire. When the mineral section shown again darkness. Similarly, the extinction position should be checked up at the other two positions during the rotation of the stage at 180 degrees and 270 degrees. If the mineral section shows illumination with the interference colors in the position when the edge or cleavage lines is parallel to either horizontal or vertical crosswire and shows darkness or extinction in a certain position during the rotation of the stage, when the edge or cleavage lines of the mineral is inclined to the crosswires, the type of extinction is identified as inclined or oblique extinction. In this case, the extinction direction, the vibration direction of the mineral coinciding with the crosswire, does not coincide with or is parallel to the edge or cleavage lines, crystallographic direction. Therefore, the type of extinction is identified as the inclined or oblique extinction. In such a case, the angle between the extinction direction, the crosswire coinciding with the vibration direction of the mineral, and the edge or cleavage line, crystallographic direction, is called the extinction angle. It is determined as follows. The stage reading is recorded at the position of the mineral section in which its edge or the cleavage lines is parallel to any of the crosswires, say horizontal crosswire, when the section shows illumination. Let the stage reading be 60 degrees. At this position, the vibration direction of the mineral are inclined to the crosswires and also to the edge or cleavage lines of the mineral section. The stage is next rotated anti-clockwise till the mineral section shows total or maximum darkness, extinction, and the stage reading is noted again. Let it be 90 degrees. At this position, the vibration directions of the mineral section coincide with the crosswires, extinction directions, which are inclined to the edge or cleavage lines of the mineral section. Then, the difference between the two readings of the stage is noted, and it is in this case 30 degrees, 90 degrees minus 60 degrees. This angle of 30 degrees is the angle between the crystallographic direction indicated by the edge or cleavage lines of the mineral section and one of the extinction directions, namely one of the vibration directions coinciding with horizontal crosswire. Since the angle measured is 30 degrees, which is less than 45 degrees, it is expressed as the extinction angle of the mineral under observation, since the extinction angle of the mineral is the angle between the crystallographic direction and the nearest extinction direction, in this case the vibration direction coinciding with the horizontal cross wire. In the measurement of extinction angles, it is to be remembered that if the angle obtained by measurement is above 45 degrees, its complementary angle, 90 degrees minus the measured angle, is expressed as the extinction angle of the mineral. But if the measured angle is 45 degrees or less than 45 degrees, this angle itself is expressed as the extinction angle of the mineral, since the extinction angle of a mineral is the angle between its crystallographic direction and the nearest extinction direction as cited before. Twinning. In a homogeneous crystal aggregate, if all the crystals occur in parallel position with their similar crystallographic directions lying mutually parallel, the case is one of parallel growth. If, on the other hand, the parallelism is only partial and the two halves of the crystal, thus related, show some of the crystallographic directions oriented in oblique disposition, the case is of twinning. In twinned crystals, the two halves occur with some re-entrant angle lying in between them. The basic nature of the atoms in crystals is to orient in definite directions, for example, parallel to 100 and 111. Rarely, arrangement of atoms is seen to reverse along certain planes, with the result optical constants and various properties like electric conductivity get reversed. Such configuration results in twinned crystals. A twin is defined by composition plane, twin axis, twin planes, and twin center. A compositional plane is a plane along which two twinned individuals are attached together, wherein there is a reflection of the lattice arrangements and crystal constants by a mirror plane. Twin axis is an axis about which various crystal constants are rotated, usually by 180 degrees. Twin plane lies normal to twin axis. Inversion about a point is called the twin center. Twins are normally defined by certain twin laws. Example, Dauphin law of quartz. In twinned crystals, depending upon the style of reversal arrangement, twins are classified into normal, parallel, and complex twins. In normal twins, the twin axis lies at right angles to the composition plane, and twin planes lie parallel to each other. Example, all-bite twin and macle or twinned octahedron in diamond and spinel. Twin axis in a parallel twin lies in the composition plane, with composition plane and twin plane disposed at right angles to each other. In a similar way, complex twin can be explained as a combination of normal and parallel twin. When two twinned individuals can be separated easily along the composition plane, they are termed as contact twins. If only two twinned individuals exist, they are simple twins. But when many individuals are attached with their composition planes parallel to each other, they are termed as polysynthetic, multiple, or lamellar twins. In some cases, the two individuals grow by cutting each other across, resulting in penetration or interpenetration twins. The two twinned individuals in such cases can hardly be separated from each other. In certain cases, composition planes of a polysynthetically twinned crystal do not lie parallel to each other, resulting in cyclic twins. Often, the symmetry of a crystal belonging to a lower symmetry group increases on twinning, and such twins are referred to as mimetic twins. Based on genetic relationship, twins are defined as growth twins, transformation twins, and gliding twins. In growth twins, twinning takes place at the time of growth of the crystal. In case of transformation twin, twinning develops subsequent to growth. Example, M twinning or crosshatch twinning in microcline and Dauphin law in quartz. If the twinning develops during a deformational event, it is called gliding twin or deformation twin. Example, twinning in corundum and cordierite. Gliding twin in corundum results in the development of parting planes. This type of twinning has great significance in distinguishing natural ruby and sapphires. The phenomenon of twinning is very well visualized in thin sections under the microscope, since within the individual components of the twins, some of the crystallographic directions are not parallel, and naturally, both the twinned halves cannot undergo extinction simultaneously. The two twinned halves show, between cross-Nichols, a sharp and straight line of separation, and while one half is in extinction, the other must exhibit interference color. The mineral plagioclase very commonly shows what is known as lamellar twinning, since, due to repeated twinning, narrow lamellae of the mineral occur in juxtaposition. Crystals of the same species growing in a melt have a tendency to get attached together, which may appear like twinned crystals. These are not twins in the true sense, but this process is called syneusis. Accessories of transmitted light microscope. The main accessories of the transmitted light microscope are quartz wedge, gypsum plate, mica plate, and universal stage or U- stage. Quartz wedge. Quartz wedge consists simply of a very thin tapering wedge, the faces of which are approximately parallel to the prism of a quartz crystal. It is mounted on a narrow glass plate marked with the letter Q and an arrow marked X, indicating that of the two directions of vibration of light in the wedge, the one which is parallel to this direction of the ray propagated with greater velocity, and if marked Z, indicates that this is the direction of vibration of the slower ray. As the thickness of the quartz increases, the sequence of the colors in the following order: violet, blue, green, yellow, orange, and red is repeated distinctly 3 times, corresponding to the first, second, and third orders, with fainter and unclear colors beyond. An important application of the quartz wedge is in determination of the order of interference colors of anisotropic minerals under crossed polars. Gypsum plate. This is a thin plate of gypsum mounted between 2 plates of glass with an arrow marked either X or Z, indicating respectively the direction of vibration of the faster or slower ray. The name sensitive tint is given to this because a slight increase of the double refraction gives a blue color, and a corresponding decrease changes the color to yellow. This is used mainly to determine the direction of vibration X or Z in the anisotropic minerals under crossed polars, and accordingly the SING, that is, negative yellow color subtraction, and positive blue character with sensitive tint color addition. Mica plate. This is a sheet of muscovite mica cleaved so thin that of the 2 rays of light passing through it, one has gained 1/4 of a wavelength in phase over the other, and is usually mounted between long and narrow glass plates. This is also known as the 1/4 wavelength, 1/4 lambda mica plate. It is used in testing an interference figure. For this, it is inserted between the polarizer and analyzer through the slot in the tube above the objective, and is so oriented that the Z direction makes an angle of 45 degrees with the planes of vibration of the Nichols. After its introduction, if the isogyres of the interference figure of a mineral in the direction of the introduction of the plate move closer, then the mineral is positive, and if they move away, it is negative. Universal U- stage. This helps in orienting the minerals in thin section in all the 3 directions by allowing the section to tilt in any desired position in space. It has either 4 or 5 axes corresponding to 4 or 5 flat rings, with the ring 5 carrying ring 4, ring 4 carrying ring 3, ring 3 carrying ring 2, and ring 2 carrying ring 1. Rings 1 and 4 rotate on vertical axes through the center of the U state. Rings 3 and 5 rotate on east-west axis, and ring 2 rotates on a north-south axis, with direction north being away and east-west being parallel to the observer. The U stage helps in determining optical constants of an anisotropic mineral, twin schemes of feldspars and other minerals, and for petrofabric study of rocks. General optical characters under transmitted light microscopy. The properties that help in mineral identification by the transmitted light microscopic study are color, habit, pleochroism, relief, cleavage, isotropism, and anisotropic properties such as twinning, interference figure, and extinction angle. Refractive index. Refractive index of a crystal is the sine of the angle of incidence divided by the sine of the angle of refraction. However, only glass and crystals in isometric system are singly refractive, while all minerals belonging to tetragonal, trigonal, hexagonal, orthorhombic, monoclinic and triclinic systems have two refractive indices. Refractive index divided by indices of each mineral is unique. There of course are overlaps in ranges, but still determination of refractive index along with other tests can help in mineral identification. The refractive index of a mineral is determined by refractometer. The instrument is designed optically to use the phenomenon of critical angle, total internal reflection, to provide direct refractive index reading and is also known as critical angle refractometer. However, the principle can only be used if the refractive index of the mineral being tested is less than the refractometer's lead glass prism, which has an refractive index of 1.86. If the mineral refractive index is greater than the refractive index of this prism, the ray will be refracted out and there will be no total internal reflection. The mineral is placed on this glass prism in such a way that one of its flat facets is in good contact of the prism. In reality, however, a contact fluid, saturated solution of sulfur in diiodomethane and tetraiodoethylene with refractive index 1.81 is used to ensure good optical contact between the gem and the lead glass prism. The principle of total internal reflection occurs as follows. As light converges from the prism onto the surface of the mineral, ray I1 and I2, which have larger angle of incidence compared to the critical angle, are reflected back into the denser prism following the laws of total internal reflection. Rays I4 and I5, whose angle of incidence is less than the critical angle, are refracted into the gem. But ray I3, which is incident just at the critical angle, travels along the interface of the two mediums. Thus, when light rays pass from a dense medium to a rarer medium of gemstone, the light rays will be reflected back from the surface of the gemstone over an arc of incident angle greater than that of critical angle of incidence. This critical angle is determined by the refractive indices of both the denser medium and the gemstone. The dense medium in the refractometer is a glass prism of known refractive index. The critical angle gives the direct measure refractive index of mineral as follows. Sine of critical angle equals refractive index of rarer medium mineral divided by refractive index of dense medium, prism of refractometer. Refractive index of mineral equals sine of critical angle into refractive index of refractometer prism. In the critical angle refractometer, the light rays arriving at the interface between the mineral and the glass prism and having an angle of incidence less than the critical angle are not reflected into the lens system. However, those rays having an angle of incidence greater than the critical angle are reflected into the lenses and illuminate a scale graduated in refractive index values. The image of the scale is inverted by a mirror and then focused by the eyepiece. The end result is viewed as a dark top section and an illuminated lower part. The horizontal shadow edge between the two parts is the measurement of the refractive index of the mineral. twinkling. In anisotropic minerals, the index of refraction differs with direction. A mineral fragment showing high relief in one direction and low relief in another is said to have variable relief, and such a mineral shows on rapid rotation of the microscope stage under plain polarized light, without using the analyzer. Variation in relief with alteration of strongly marked and slightly marked borders giving a twinkling effect, and hence this phenomenon is called twinkling. Calcite is a very good example of a mineral showing twinkling. In calcite, the refractive index for the ordinary ray is 1.66, for the extraordinary ray is 1.49, and the refractive index of Canada balsam is 1.54. The refractive index 1.66 for ordinary ray is very much higher than that of balsam, while that 1.49 for the extraordinary ray is lower than that of balsam. Therefore, the rotation of the microscope stage brings about a strong change from high positive relief to low relief, which may be positive or negative, resulting in the alteration of strongly marked and slightly marked borders. Twinkling. Birefringence. The difference between the two refractive index values is known as the birefringence. This is best seen in doubly refracting minerals like calcite, where the refractive index in c-axis direction is 1.4864. Epsilon, light vibrating in this direction, is known as the extraordinary ray or E-ray, and in the direction of A-axis, refractive index is 1.6585. Omega, light vibrating in this direction, is known as ordinary ray or O-ray. It is also expressed as N2 minus N1, wherein N2 and N1 stand for the values of maximum and minimum refractive indices, respectively, in the crystal. The difference in refractive index is also abbreviated as DR, double refraction, or delta. The difference in values between the maximum and minimum refractive index, epsilon and omega in tetragonal and hexagonal crystals, and alpha in orthorhombic, monoclinic and triclinic crystals, is smaller in some crystals. Example, apatite, quartz and feldspar. Birefringence weak, and greater in some other crystals. Example, rutile and calcite. Birefringence extreme. When faceted stones characterized by strong birefringence, example, peridot, zircon and sphene, are viewed from the table facet, the culate and back facets appear in two sets, doubling of the back facets. A 10x loop is quite handy to observe the doubling effect. If the table is cut perpendicular to the optic axis, the stone has to be tilted to notice the doubling effect. The doubling effect, however, is not obvious in the stones having weaker birefringence. Example, apatite. Conclusion. The petrological microscope is a basic lab tool for a geologist which assists in identifying the optical properties of the individual minerals or the minerals present in the rock. Refractive index is an important optical property which helps in the identification of minerals using refractometer. In fact, the minerals which possess similar certain other optical or physical properties can be distinguished with the help of refractive index. The property of twinkling is useful in identifying some of the anisotropic minerals. In order to identify doubly refracting minerals, the optical property birefringence plays a significant role. Thus, petrological microscope is an unavoidable tool for the identification of minerals and minerals present in rocks from the properties depending on light. Some of the minerals which may not be identified with the help of physical properties can be identified with the optical properties. The optical properties mentioned not only serves to identify the minerals but also helps in distinguishing the minerals, showing the identical optical properties.